Hello and welcome to a quiet corner of the universe, where the impossible becomes inevitable and the hidden becomes hauntingly beautiful. Tonight, we're diving deep into one of the most elegant and unsettling theories in modern physics, one that suggests every moment of your life creates countless parallel worlds, each containing a different version of you, living out every possible outcome of every decision you never made. Picture this. Right now, as you listen to these words, there might be another version of you in a parallel universe who decided not to click on this video, and another who's watching it on a different device, in a different room, perhaps even in a different country. According to quantum decoherence theory, these aren't just philosophical thought experiments or science fiction fantasies. They're as real as the world you're experiencing right now. The only catch, you'll never, ever be able to see them. This is the story of quantum decoherence, the hidden mechanism that creates parallel worlds while simultaneously ensuring they remain forever beyond our reach. It's a tale of cosmic hide and seek, where reality splits into countless branches every fraction of a second, yet each branch remains perfectly isolated from all the others. And tonight we're going to explore why this strange, beautiful, and slightly terrifying process might be the most fundamental feature of our universe. Now, I do hope this journey isn't so fascinating that it keeps you awake longer than intended. But if it does, at least you'll be pondering one of the most profound mysteries science has ever uncovered. Before we begin this gentle descent into quantum wonderland, if you find these explorations of the universe's deepest secrets soothing to your curious mind, I'd be grateful if you let me know by tapping the like button. And if you'd like to join me on more voyages into the strange and beautiful corners of reality, consider subscribing. I love hearing from fellow travellers in the comments, so please share where in the world you're listening from tonight and what time it is in your corner of existence. Take a deep breath, settle in, and let's begin our quiet journey into the quantum realm, where parallel worlds are born every instant, yet remain forever hidden in the shadows of what might have been. Imagine you're holding a soap bubble in your hands. It shimmers with all the colours of the rainbow, its surface dancing with interference patterns that shift and change with every breath of air. This delicate sphere exists in a perfect balance between order and chaos, beauty and fragility. Now imagine that this bubble represents the quantum state of every particle in the universe, constantly trembling on the edge between multiple possibilities. This is the world that quantum mechanics reveals to us, a realm where particles don't just exist in one place or have one definite property, but instead exist in what physicists call a superposition. It's as if that soap bubble could be in multiple places at once, reflecting different colours simultaneously, until something comes along to pop it into a single, definite state. But here's where the story becomes truly mysterious. In the quantum world, that soap bubble doesn't simply pop and disappear. Instead, when it encounters its environment, something far stranger happens. The bubble splits, creating countless identical copies of itself, each taking on a different colour, a different position, a different fate. And once these bubbles separate, they can never touch again, never compare notes, never even know that the others exist. This is the essence of quantum decoherence, and it's happening around you, inside you, and throughout the entire universe, billions of times every second. Every quantum system, from the electrons spinning around atomic nuclei to the photons streaming from distant stars, exists in this delicate state of multiple possibilities until it encounters the world around it. The term decoherence itself is beautifully descriptive. Think of a symphony orchestra where every musician is perfectly synchronized. their instruments creating harmonious interference patterns that produce beautiful music. Now imagine that each musician begins to play slightly out of phase with the others, their individual parts becoming lost in a cacophony of competing sounds. The music hasn't stopped, but the coherent harmony that made it beautiful has been destroyed. The orchestra is still playing, but now each musician might as well be in a different concert hall. This is precisely what happens to quantum systems when they interact with their environment. The quantum coherence, that delicate synchronization between different possible states, gets scrambled and spread out among countless environmental variables. The system doesn't collapse into a single state, as some interpretations of quantum mechanics suggest. Instead, it branches into multiple parallel versions, each one perfectly real, but forever unable to influence the others. The man who first glimpsed this strange truth was David Bohm, though he didn't use the term decoherence when he introduced the concept in 1951. Bohm called it the destruction of interference in the process of measurement, a phrase that captures both the loss of quantum coherence and the birth of classical reality. He understood that something profound was happening when quantum systems encountered the macroscopic world, something that went beyond simple wave function collapse. But it wasn't until 1970 that German physicist H. Dieter Zeh began to develop the modern theory of decoherence. Zeh had a radical insight. What if the quantum wave function never actually collapses? What if all those different possibilities continue to exist but become so entangled with the environment that we can only see one branch of reality at a time? This idea was revolutionary because it suggested that the universe doesn't choose between different quantum possibilities. Instead, it embraces all of them simultaneously, creating parallel worlds for every possible outcome. The reason we don't see these other worlds isn't because they don't exist, but because decoherence has made them inaccessible to us, hidden behind an impenetrable veil of environmental entanglement. To understand how parallel worlds emerge from quantum decoherence, we need to take a gentle journey into the mathematical heart of the theory. Don't worry, we won't get lost in complex equations. Instead, think of mathematics as the language the universe uses to tell us its deepest secrets. And like any language, once you understand the basic vocabulary, the poetry begins to reveal itself. At the center of quantum mechanics lies something called the wave function, often represented by the Greek letter psi. If you've ever dropped a pebble into a still pond and watched the ripples spread outward, you've seen something analogous to a wave function. But unlike water waves, quantum wave functions exist in an abstract mathematical space where they can represent multiple states simultaneously. Imagine you have a coin that you're about to flip. In our everyday classical world, we know that the coin is either heads or tails at any given moment, even if we can't see which side it's showing. But in the quantum world, the coin exists in a superposition of both heads and tails simultaneously. The wave function describes this strange state mathematically, assigning probabilities to each possible outcome. Now, here's where decoherence enters the picture. When that quantum coin interacts with its environment, perhaps through air molecules bumping against it or photons bouncing off its surface, something remarkable happens. The simple wave function that described heads plus tails becomes entangled with the wave functions of all those environmental particles. This entanglement is like a cosmic game of telephone, where the quantum information about the coin's state gets passed from particle to particle throughout the environment. But unlike the childhood game, where the message gets distorted in quantum entanglement, the information is preserved perfectly. It's just spread out among so many particles that it becomes practically impossible to gather it all back together. The mathematical description of this process involves something called a density matrix, which is essentially a way of describing quantum systems when you can't keep track of everything that's happening in their environment. When physicists calculate what happens to our quantum coin after it becomes entangled with its surroundings, they find something beautiful and strange. The coin doesn't collapse into either heads or tails. Instead, the mathematics shows that both outcomes continue to exist, but in separate branches of reality that can no longer interfere with each other. It's as if the universe splits into two parallel versions, one where the coin landed heads and another where it landed tails. Each branch is equally real, equally valid, and equally unaware of the other's existence. This branching process happens incredibly quickly. For most macroscopic objects, decoherence occurs in time frames so short they're almost impossible to imagine. We're talking about timescales measured in tiny fractions of a second, periods so brief that light itself can barely travel the width of an atom. In these impossibly short moments, the quantum superposition that might have existed for a microscopic particle gets entangled with countless environmental degrees of freedom, creating the illusion of a single, definite, classical outcome. But the mathematics tells us that this is indeed an illusion. All the other possibilities are still there, playing out in parallel branches of reality that have become decorrelated from our own. The wave function of the entire universe, including all possible versions of the coin flip and all possible environmental configurations, continues to evolve according to the fundamental equations of quantum mechanics. Recent computational studies have shown that this branching process is robust and universal. When physicists simulate large quantum systems interacting with their environments, they consistently find that classical behavior emerges naturally from quantum dynamics. The parallel worlds aren't added to the theory as an extra assumption. They emerge inevitably from the mathematics itself, like shadows cast by the light of quantum mechanics. One of the most fascinating aspects of quantum decoherence is how dramatically the timescales can vary depending on the system involved. It's as if the universe operates on multiple clocks simultaneously, some ticking so fast they measure the birth and death of parallel worlds in the blink of an eye, others running so slowly that quantum coherence can persist for minutes or even hours. Consider the humble nuclear spin, nestled deep within an atomic nucleus, where it's shielded from most environmental disturbances. These quantum systems can maintain their coherence for remarkably long periods, sometimes several minutes in laboratory conditions. During this time, a nuclear spin can exist in a genuine quantum superposition, simultaneously pointing in multiple directions at once, like a compass needle that somehow points north, south, east, and west all at the same time. But venture into the realm of optical systems, where ions interact with electromagnetic fields and photons, and the story changes dramatically. Here, decoherence occurs in mere milliseconds, a time frame that feels instantaneous to us, but represents millions of quantum interactions at the atomic level. In these brief moments, the delicate quantum superpositions that might exist in a laboratory setting get entangled with their surroundings and branch into parallel worlds faster than a hummingbird's wing beat. At the extreme end of this spectrum, we encounter systems where particles directly exchange energy and momentum through scattering processes. In these violent quantum encounters, decoherence can occur in time frames measured in units so small they stretch our ability to comprehend them. We're talking about periods of time so brief that even light, travelling at its maximum possible speed, can cover distances smaller than the nucleus of an atom. These vastly different timescales reveals something profound about the nature of decoherence. The speed at which parallel worlds are born depends on how strongly a quantum system couples to its environment. It's like the difference between a whispered conversation in a quiet library and a shout in a bustling marketplace. In the library, the whisper might carry across the room intact, but in the marketplace, it gets lost in the noise almost immediately. This relationship between coupling strength and decoherence time has practical implications for our understanding of why the classical world appears so stable and definite. Large, complex objects, like tables, chairs, and human beings, are constantly interacting with their environment through countless quantum channels. Every photon that bounces off their surface, every air molecule that collides with them, every thermal vibration that passes through their structure contributes to the decoherence process. The result is that macroscopic objects decohere almost instantaneously, their quantum superpositions branching into parallel worlds so quickly that we never get a chance to observe the branching process itself. By the time our measuring instruments or our senses can register what's happening, the parallel worlds have already separated and become mutually invisible. But here's the truly remarkable part. Even though these different timescales create different rates of world splitting, the process itself is universal. Whether we're talking about a nuclear spin maintaining coherence for minutes, or a scattering event creating new worlds in attoseconds, the underlying mechanism is the same. Quantum information spreads from the system of interest into the environment, creating entangled correlations that effectively split reality into parallel branches. This universality suggests that parallel world creation isn't a rare or exotic phenomenon confined to specially prepared laboratory conditions. It's happening everywhere, all the time, at every scale of reality. The coffee cup on your desk is constantly branching into parallel versions as thermal fluctuations and electromagnetic interactions entangle it with its surroundings. The cells in your body are splitting into quantum alternatives as biochemical processes unfold. Even the thoughts in your mind, if they have any quantum component, might be creating parallel versions of your consciousness in adjacent branches of reality. The universe, it seems, is not just stranger than we imagine. It's stranger than we can imagine, operating on timescales both impossibly fast and remarkably slow, creating parallel worlds with every tick of its quantum clock, yet keeping those worlds forever hidden from each other through the elegant mechanism of decoherence. As we continue our journey deeper into this quantum wonderland, we'll explore how this constant branching process relates to one of the most famous thought experiments in all of physics, Schrödinger's cat. We'll discover how a simple setup involving a cat, a box, and a quantum system reveals the profound implications of decoherence theory and shows us why parallel worlds, though invisible to us, might be the most natural way to understand the strange reality we inhabit. But that's a story for our next chapter, where we'll gently open the box and peer inside to see what quantum mechanics has to say about life, death, and the countless parallel worlds where both outcomes unfold simultaneously. Until then, rest easy knowing that somewhere in the vast quantum multiverse, every possible version of your story is being written, each one as real and valid as the one you're living right now. I hope you'll join me as we continue this exploration into the hidden architecture of reality, where parallel worlds bloom like flowers in an infinite garden, beautiful and unreachable, yet somehow essential to everything we are and everything we might become. And if you're curious about what happens to consciousness itself in this strange quantum multiverse, you might find our previous exploration particularly thought-provoking. Quantum immortality terrifies scientists because consciousness might never end. There's something almost poetic about the way quantum mechanics chose a cat to illustrate one of its most profound paradoxes. Perhaps it's fitting that an animal known for its mysterious behaviour, its ability to seem present and absent at the same time, should become the star of physics' most famous thought experiment. In 1935, Erwin Schrödinger introduced us to a hypothetical feline that would forever change how we think about the boundary between the quantum and classical worlds. Picture a cat sealed inside a box, completely isolated from your observation. Inside this box is a diabolical device, a Geiger counter connected to a hammer that will smash a flask of poison if it detects the decay of a single radioactive atom. The radioactive sample is carefully chosen so that in 1 hour there's exactly a 50% chance that one atom will decay. According to quantum mechanics, until someone opens the box to observe the outcome, the atom exists in a superposition of both decayed and not decayed states simultaneously. This is where the paradox becomes almost surreal. If we take quantum mechanics seriously, then the cat itself must also exist in a superposition of alive and dead states, at least until the moment someone opens the box and makes an observation. Schrödinger designed this thought experiment to highlight what he saw as the absurdity of applying quantum principles to macroscopic objects. Surely, he argued, cats cannot be both alive and dead at the same time. But here's where decoherence theory offers us a startlingly different perspective, one that Schrödinger himself couldn't have anticipated. The cat paradox dissolves not because quantum mechanics fails at macroscopic scales, but because decoherence ensures that macroscopic superpositions branch into parallel worlds so quickly that we never observe them directly. Let's follow the story step by step, through the lens of decoherence theory. When the radioactive atom is placed in the box, it genuinely exists in a quantum superposition of decayed and not decayed states. This isn't just our ignorance about which state it's in. According to quantum mechanics, both states are equally real until decoherence occurs. Now, as time passes, this quantum atom doesn't exist in isolation. It's surrounded by air molecules, bathed in thermal radiation, and coupled to the Geiger counter through electromagnetic fields. Every one of these interactions spreads the quantum information about the atom's state into the environment. The superposition doesn't collapse into one outcome or the other. Instead, it branches. In one branch of reality, the atom decays early in the experiment. The Geiger counter detects this decay, triggers the hammer, and the poison is released. In this branch, the cat dies. But in another, equally real branch, the atom doesn't decay during the experimental period. The Geiger counter remains silent, the hammer stays still, and the cat continues to purr contentedly in its box. Here's the crucial insight that decoherence theory provides. These branches separate so quickly that they become mutually unobservable almost immediately. The quantum information about the atom state gets entangled with the measuring device, then with the air molecules in the box, then with the thermal vibrations of the box walls, spreading outward like ripples in a pond until it's distributed across countless environmental degrees of freedom. Each branch contains a complete, consistent, classical reality. In the branch where the cat died, there's a clear, causal chain. Atom decayed, detector clicked, hammer fell, poison released, cat expired. Every air molecule in the box, every photon bouncing around, Every piece of the measuring apparatus tells the same coherent story. Similarly, in the branch where the cat lived, all the physical evidence points to a consistently different outcome. But here's what makes this truly extraordinary. Both cats are equally real. The living cat in one branch and the dead cat in the other are not just theoretical possibilities or mathematical abstractions. They're both genuine physical realities, existing in parallel branches of the universal wave function. The reason we see only one outcome when we open the box isn't because the other possibility doesn't exist, but because decoherence has made the two branches mutually inaccessible. This resolution of the cat paradox reveals something profound about the nature of observation in quantum mechanics. When we open the box, we don't cause the wave function to collapse into one state or another. Instead, we become entangled with one of the already existing branches. Our consciousness, our measuring instruments, our entire local environment becomes correlated with either the living cat branch or the dead cat branch, but never with both simultaneously. The moment we lift the lid and peer inside, we discover which branch of reality we've been part of all along. If we see a living cat, it's because our timeline, our branch of the multiverse, happens to be the one where the atom didn't decay during the experimental period. Somewhere else in the vast expanse of parallel worlds, another version of us is opening the same box and finding a very different outcome. This perspective transforms the act of measurement from a mysterious collapse of possibilities into something more like the unveiling of a predetermined but previously hidden correlation. The measurement doesn't create the outcome. It reveals which branch of an already branched reality we happen to inhabit. Every quantum measurement, from the simplest spin detection to the most complex particle physics experiment, works the same way, revealing our location in the vast tree of parallel worlds, rather than forcing the universe to choose between alternatives. If Schrödinger's cat shows us how decoherence creates parallel worlds in macroscopic systems, then the double slit experiment reveals how this process works at its most fundamental level. This elegantly simple setup has been called the heart of quantum mechanics, and for good reason. It demonstrates with crystalline clarity how the act of observation creates the branching that lies at the core of decoherence theory. Imagine standing before a barrier with two narrow slits cut into it, beyond which lies a detection screen. Now, one by one, you send particles toward this barrier. In our everyday classical world, we'd expect each particle to pass through one slit or the other, creating two distinct bands of hits on the screen behind. But quantum mechanics has a different story to tell. When no one is watching, when no detector monitors which slit each particle passes through, something magical happens. The particles create an interference pattern on the screen, a series of alternating bright and dark bands that can only be explained if each individual particle somehow passes through both slits simultaneously. This wave-like behavior persists even when particles are sent one at a time, separated by minutes or hours. Somehow, each individual particle interferes with itself, as if it explores both possible paths through the barrier. This phenomenon becomes even more mysterious when we consider what happens the moment we try to determine which slit each particle actually uses. Place a detector near one of the slits, and the interference pattern vanishes instantly. The particles begin behaving like classical objects, passing through one slit or the other, but never both. The very act of observation seems to change the fundamental nature of reality. Through the lens of decoherence theory, this transformation takes on a completely different meaning. When no detectors are present, the particle genuinely exists in a quantum superposition of taking both paths simultaneously. But the moment a detector is introduced, decoherence begins its work. The particle becomes entangled with the detecting apparatus, which in turn couples to its environment, spreading the quantum information about which path was taken throughout the surrounding space. Here's the crucial insight. The interference pattern doesn't disappear because observation collapses the wave function. Instead, it disappears because the universe branches into parallel worlds, one for each possible path the particle might take. In one branch, the particle passes through the left slit and is detected there. In another branch, it passes through the right slit and triggers the right detector. Each branch contains observers who see a perfectly consistent classical outcome, but the branches can no longer interfere with each other because decoherence has separated them. The detector acts as an amplifier of decoherence, taking the microscopic quantum information about the particle's path and spreading it into macroscopic classical information that gets entangled with the environment. This amplification process is what makes the branching irreversible and ensures that the parallel worlds remain forever separate. But here's where the story becomes truly remarkable. Even in the branched reality, both paths still exist. In one branch of the multiverse, experimenters consistently observe particles passing through the left slit. In another branch, different versions of those same experimenters observe particles taking the right path. Each branch develops its own consistent history, its own scientific literature, its own understanding of which path the particles followed. The absence of interference isn't evidence that the particle really took one path or the other. Instead, it's evidence that decoherence has created separate worlds where different path information is accessible to observation. The wave function describing all possible paths continues to evolve according to the fundamental equations of quantum mechanics, but it now describes multiple non-interfering branches of reality rather than a single interfering superposition. Recent experiments have pushed this phenomenon to extraordinary limits. Scientists have demonstrated interference effects with molecules containing thousands of atoms, with systems large enough that they begin to approach the boundary between quantum and classical behaviour. In each case, the pattern is the same. As long as which path information remains hidden from the environment, interference persists. But the moment that information leaks out through any channel, decoherence sets in and the parallel worlds separate. This reveals something profound about the role of information in quantum mechanics. It's not consciousness or human observation that causes the branching. It's the irreversible flow of information from quantum systems into their classical environments. Every photon that bounces off a particle carries which path information. Every air molecule that gets jostled by a moving detector spreads that information further. Every thermal vibration that correlates with the experimental setup contributes to the decoherence process. The double-slit experiment, viewed through the lens of decoherence theory, becomes a window into the fundamental architecture of reality. It shows us that the universe doesn't choose between different possibilities. Instead, it embraces all of them, creating parallel branches where every possible outcome unfolds in its own consistent timeline. We see only one branch, not because the others don't exist, but because decoherence has made them inaccessible to our observation. There's something almost breathtaking about the speed at which parallel worlds are born. In the time it takes you to blink your eyes, trillions upon trillions of quantum interactions occur throughout your body, each one potentially creating new branches in the vast tree of parallel realities. The universe doesn't wait for dramatic moments or important decisions to split into alternatives. It's branching constantly, relentlessly at every scale and in every corner of existence. To appreciate these timescales, we need to journey into realms of speed that challenge our everyday intuition. Consider a simple interaction between two electrons in an atom. When these particles scatter off each other, exchanging momentum and energy, the decoherence that creates parallel worlds can occur in time frames measured in attoseconds. An attosecond is to a second what a second is to about 30 million years. In these impossibly brief moments, the quantum superposition of different scattering outcomes branches into separate worlds, each containing electrons with slightly different trajectories. But not all quantum systems succumb to decoherence at these breakneck speeds. Deep within atomic nuclei, nuclear spins exist in a more sheltered environment, partially isolated from the electromagnetic chaos that surrounds them. These quantum systems can maintain their coherent superpositions for minutes or even hours under the right conditions. During this extended period, a nuclear spin genuinely exists in multiple orientations simultaneously, like a quantum compass pointing in all directions at once. This vast range of decoherence timescales reveals something beautiful about the quantum world. The universe operates like a symphony with multiple tempos playing simultaneously. Some sections race along at impossibly fast speeds, creating and destroying parallel worlds faster than light can travel across an atomic nucleus. Other sections unfold with stately grandeur, allowing quantum coherence to persist long enough for human experimenters to manipulate and observe it. The factors that determine these timescales are elegant in their simplicity. The strength of coupling between a quantum system and its environment acts like a volume knob for decoherence. Systems that interact strongly with their surroundings branch into parallel worlds quickly. Those that remain more isolated can maintain their quantum superpositions for extended periods. Temperature plays a crucial role as well. In the frigid depths of space far from any star, quantum systems can maintain coherence for cosmic ages. But in the warm, bustling environment of a living cell, thermal motion constantly jostles quantum states, accelerating the decoherence process. It's as if the universe has different climate zones for quantum behavior, from the Arctic preservation of deep space to the tropical chaos of warm, dense matter. The size and complexity of a quantum system also influence how quickly it branches into parallel worlds. A single electron, with its relatively simple quantum state, might maintain coherence longer than a complex molecule with thousands of internal degrees of freedom. Each additional particle, each new way the system can interact with its environment, provides another channel through which quantum information can leak out and create decoherence. This relationship between complexity and decoherence helps explain why macroscopic objects appear so classically definite. A coffee cup sitting on your desk isn't just a single quantum system. It's an almost incomprehensibly complex collection of atoms, molecules, and electrons, each one coupled to countless others through electromagnetic forces, thermal vibrations, and chemical bonds. The cup is constantly exchanging photons with its surroundings, absorbing and emitting thermal radiation, vibrating in response to sound waves and mechanical disturbances. All of these interactions create decoherence channels, pathways through which quantum information flows from the cup into its environment. The result is that any quantum superposition involving the cup's macroscopic properties branches into parallel worlds almost instantaneously. By the time your eyes register the cup's presence, it has already split into countless parallel versions, each one appearing perfectly classical and definite within its own branch of reality. But here's what makes this process truly extraordinary. The branching never stops. Even as you read these words, your body is splitting into parallel versions as quantum processes unfold within your cells. The neurons firing in your brain, the chemical reactions powering your metabolism, the photons entering your eyes from the screen. All of these processes involve quantum mechanics and therefore create decoherence. Each interaction spawns new branches in the multiverse, new versions of you experiencing slightly different outcomes. The implications are staggering. If decoherence theory is correct, then the version of you reading this sentence is just one of countless parallel selves, each one emerging from the quantum interactions that occurred in your brain and body over the past few moments. Some of these parallel selves might be having slightly different thoughts, noticing different aspects of these words, or experiencing marginally different emotional responses to these ideas. Yet none of these parallel selves can ever meet or compare notes. Decoherence ensures that once the branches separate, they remain forever isolated from each other. You are living in just one thread of a vast tapestry of parallel lives, unable to see the countless other threads that run alongside your own, each one equally real but forever beyond your reach. As we continue our exploration of this strange quantum multiverse, we'll discover how consciousness itself fits into this picture of constantly branching realities. We'll explore whether the mind, that most mysterious aspect of human existence, might itself be subject to the same quantum branching that governs the rest of the physical world. It's a question that touches on the deepest mysteries of existence. What it means to be conscious, what it means to be you, and whether there might be countless other versions of your consciousness exploring different branches of reality in parallel worlds you'll never see. There's a question that emerges from the depths of quantum decoherence theory, one that philosophers and physicists have been grappling with for decades, often in whispered conversations at the edges of academic conferences. If the universe is constantly splitting into parallel branches, if every quantum interaction creates new worlds where different outcomes unfold, then what happens to consciousness itself? Are there parallel versions of your awareness, your thoughts, your very sense of self, experiencing different realities in worlds you'll never know exist? This isn't just an abstract philosophical puzzle. It strikes at the heart of what it means to be you, to have experiences, to feel the weight of decisions and the flow of time. When you chose to watch this video instead of doing something else, did other versions of your consciousness make different choices? And if so, what does that tell us about the nature of free will, identity, and the continuity of experience? The relationship between consciousness and quantum mechanics has always been a delicate dance between hard science and profound mystery. Some physicists argue that consciousness itself might play a fundamental role in quantum measurement, that the act of observation by a conscious mind somehow selects which branch of reality becomes real. But decoherence theory suggests something far more subtle and perhaps more unsettling. Consider what happens in your brain as you process these words. Neurons fire in complex patterns, neurotransmitters flow across synapses, and electrical signals cascade through networks of interconnected cells. Many of these processes involve individual molecules, ions crossing cell membranes, quantum states of electrons in organic compounds. If quantum mechanics governs these microscopic events, then your thoughts themselves might be subject to the same branching that creates parallel worlds throughout the rest of the universe. But here's where the story becomes truly fascinating. Unlike the simple quantum systems we've discussed, your brain is an incredibly complex classical system that maintains its structure through constant interaction with its environment. The warm, wet environment of your neural tissue creates rapid decoherence for most quantum processes. Any quantum superpositions that might arise in individual molecules or cellular components branch into separate worlds so quickly that they're unlikely to affect the large-scale patterns of neural activity that seem to correlate with conscious experience. This suggests something both comforting and strange about the nature of consciousness in a quantum multiverse. Your stream of awareness, the continuous flow of thoughts and sensations that feels so intimately yours, likely remains coherent across the quantum branching process. When the universe splits due to a quantum measurement in a distant laboratory, your consciousness doesn't split with it. You continue as a single unified awareness, but now existing in one specific branch of a newly divided reality. However, there's a more subtle possibility that physicists and philosophers have begun to explore. What if consciousness, rather than being split by quantum branching, serves as a kind of selector that determines which branch we experience, not through any mystical intervention, but through the simple fact that conscious observers can only be aware of branches where their brains function normally, where the delicate chemistry of neural activity proceeds in ways that support organized thought. This idea leads to some profound implications. Every moment of your conscious experience might represent your awareness following the path through the quantum multiverse, where your brain continues to function optimally. In parallel branches where random quantum events disrupt crucial neural processes, versions of you might exist but lack coherent consciousness. Your stream of awareness naturally flows along the branches where it can continue to exist, creating the subjective experience of a continuous, unbroken timeline. But consciousness in a quantum multiverse raises even deeper questions about personal identity. If there are parallel versions of you in adjacent branches of reality, versions that diverged only moments ago due to quantum events in your brain or body, which one is the real you? Are they all equally valid manifestations of your identity? Or is there something special about the particular branch you happen to be experiencing right now? These questions become especially poignant when we consider the nature of memory and decision-making. Your memories of the past, your sense of having made certain choices and experienced specific events, exist only within your current branch of reality. In parallel branches, versions of you might have slightly different memories, might recall conversations that went differently, or decisions that led to alternative outcomes. Each version would feel equally convinced that their memories represent the true history of their existence. The implications extend to every aspect of human experience. The love you feel for family and friends, the satisfaction of accomplishments, the weight of regrets and disappointments, all of these emotional realities exist within your specific branch of the multiverse. In parallel worlds, other versions of you might be experiencing different relationships, different career paths, different joys and sorrows. The life you consider uniquely yours is just one thread in an infinite tapestry of possible lives. Yet there's something almost liberating about this perspective. If countless versions of you are exploring different possibilities across parallel branches of reality, then in some sense, every choice you might have made is being made. Every path you wonder about, every alternative life you sometimes imagine, might be unfolding in adjacent worlds. The opportunities you missed in this timeline might be opportunities seized in another. The words you wish you had spoken might be echoing in parallel conversations you'll never hear. This doesn't diminish the importance of your choices or experiences in this branch of reality. If anything, it makes them more precious, more uniquely yours. The specific combination of quantum events that led to your particular stream of consciousness, the exact sequence of branching points that created your timeline, has never existed before and will never exist again. You are not just one of countless parallel selves. You are the unique convergence of quantum possibilities that created this particular moment of awareness. One of the most enduring mysteries in quantum mechanics has been the observer effect, the strange phenomenon where the act of measurement seems to fundamentally alter the behavior of quantum systems. For decades, this has led to puzzling questions about the role of consciousness in physics. Does observation by a human mind somehow cause wave functions to collapse? Are conscious observers special in some fundamental way that allows them to influence quantum reality? Decoherence theory offers us a radically different perspective on these questions, one that removes consciousness from its central role while revealing something even more profound about the nature of observation and reality. The observer effect, it turns out, isn't really about observers at all. It's about information, entanglement, and the irreversible flow of quantum data from microscopic systems into macroscopic environments. Let's revisit the classic example of electron spin measurement. When we set up an apparatus to measure whether an electron is spinning up or down, we're not just passively observing a pre-existing property. We're creating a situation where the electron's quantum state becomes entangled with a measuring device, which in turn becomes entangled with its environment, spreading the measurement information throughout countless degrees of freedom. The crucial insight is that this process doesn't require a conscious observer to be present. The measurement occurs the moment the electron interacts with the detecting apparatus, regardless of whether any human is watching or even whether the results are ever recorded or read. The observation is really just the physical interaction between quantum systems and their classical environments. But here's where decoherence theory reveals something beautiful about the nature of measurement. When that electron spin measurement occurs, the universe doesn't randomly select one outcome over another. Instead, it branches into parallel realities where both outcomes happen simultaneously. In one branch, the detector registers spin up and all the associated classical correlations cascade through the environment. In another branch, the detector shows spin down and a different set of correlations propagates outward. Each branch develops its own consistent classical reality. In the spin-up branch, every piece of the measuring apparatus, every photon bouncing around the laboratory, every air molecule jostled by thermal motion, tells the same coherent story about the measurement outcome. Scientists in that branch will find consistent results when they check their instruments, analyze their data, and compare notes with colleagues. The same is true in the spin-down branch, but with systematically different results. This perspective transforms our understanding of scientific measurement from a process of discovery to something more like navigation. When scientists perform an experiment, they're not forcing nature to reveal hidden truths. Instead, they're determining which branch of an already branched multiverse they happen to inhabit. The measurement reveals their location in the vast tree of parallel realities rather than creating the reality they observe. This has profound implications for how we think about scientific knowledge itself. Every experimental result, every confirmed theory, every piece of evidence that supports our understanding of the natural world exists within our specific branch of the multiverse. In parallel branches, scientists might have obtained different data, leading to alternative theories and different understandings of natural law, but this doesn't make science arbitrary or subjective. Within each branch, the laws of physics remain consistent and predictive. The parallel worlds don't communicate with each other, so the scientific method works just as well for exploring the physics of our particular branch as it would if that branch were the only reality. The fact that other branches might have different experimental outcomes doesn't undermine the validity of science within our own timeline. In fact, decoherence theory might explain why science works at all. The rapid decoherence of macroscopic measuring instruments ensures that each branch develops stable, consistent classical properties. This stability creates the reproducible phenomena that makes scientific investigation possible. Without decoherence, macroscopic objects might remain in quantum superpositions, making it impossible to obtain definite measurement results or establish consistent natural laws. The observer effect, reimagined through decoherence theory, becomes a testament to the fundamental interconnectedness of all physical systems. Every measurement creates correlations that spread throughout the environment, linking the microscopic quantum world to the macroscopic classical realm. These correlations don't just record information about quantum systems. They create the classical reality in which that information can exist and be processed. Consider what happens when you read the result of a quantum measurement on a computer screen. The photons entering your eyes carry information that originated in a quantum system, passed through measuring apparatus, was processed by electronic circuits, and finally reached your visual cortex. This entire chain of information transfer involves countless quantum interactions, each one creating decoherence and potentially contributing to the branching structure of parallel worlds. By the time the measurement result reaches your consciousness, it has been amplified from a single quantum event into a macroscopic classical signal that involves billions of particles and countless environmental degrees of freedom. The branching that created parallel outcomes occurred much earlier in this chain, at the moment the original quantum system became entangled with the measuring device. This reveals something profound about the role of consciousness in quantum mechanics. Our awareness doesn't create quantum measurement outcomes, but it does represent the final stage in a long chain of amplification and decoherence. Consciousness exists at the classical end of this process, experiencing the stable, definite outcomes that emerge after quantum information has been spread throughout macroscopic environments. In laboratories around the world, scientists and engineers are engaged in a quiet revolution that brings the theoretical insights of decoherence theory into practical contact with everyday technology. They're not trying to visit parallel worlds or communicate with alternate versions of themselves. Instead, they're learning to harness, control, and sometimes fight against the very processes that create those hidden realities. Quantum computing represents perhaps the most ambitious attempt to exploit quantum mechanics for technological advantage. At its heart, a quantum computer is a delicate dance with decoherence, an attempt to maintain quantum superpositions long enough to perform calculations that would be impossible on classical machines. Every qubit in a quantum computer exists in a superposition of 0 and 1 simultaneously, allowing quantum algorithms to explore multiple computational paths in parallel. But here's the exquisite challenge. The moment these quantum superpositions interact with their environment, decoherence sets in, and the parallel computational paths branch into separate worlds. In one branch, the computer follows one set of calculations. In another branch, it explores different possibilities. The quantum advantage disappears as the computation splits into classical alternatives rather than maintaining coherent quantum parallelism. This makes quantum computing a race against time, a desperate attempt to perform useful calculations before decoherence destroys the delicate quantum coherence that makes quantum algorithms possible. Current quantum computers must be cooled to temperatures colder than outer space and isolated from electromagnetic interference to extend the coherence time of their qubits. Even under these extreme conditions, quantum computations must typically complete within microseconds before environmental noise causes irreversible decoherence. The strategies that scientists use to combat decoherence reveal the deep connections between theoretical physics and practical engineering. Quantum error correction schemes encode quantum information redundantly across multiple qubits, allowing the detection and correction of errors caused by decoherence. Dynamical decoupling techniques apply precisely timed pulses to cancel out environmental noise. Topological qubits, still largely theoretical, would encode quantum information in global properties of quantum systems that are inherently resistant to local environmental disturbances. But quantum computing isn't the only technology wrestling with decoherence. Quantum sensors, which use quantum superpositions to detect incredibly subtle changes in magnetic fields, gravitational waves, or other physical phenomena, face similar challenges. The very sensitivity that makes these devices useful also makes them vulnerable to environmental noise that can destroy their quantum coherence. Recent breakthroughs in quantum sensing have shown that scientists can actually use decoherence to their advantage. By carefully controlling how quantum systems interact with their environment, researchers can create sensors that become more sensitive as they begin to decohere. It's like learning to listen to the whispers of parallel worlds as they separate from our own, extracting useful information from the very process that makes those worlds inaccessible. These technological applications of decoherence theory have practical implications that extend far beyond laboratory experiments. Quantum-enhanced medical imaging might soon allow doctors to see inside the human body with unprecedented clarity. Quantum sensors could detect gravitational waves from the earliest moments after the Big Bang, revealing secrets about the birth of our universe. Quantum computers might solve optimization problems that could revolutionize everything from drug discovery to financial modeling. Yet all of these technologies must grapple with the fundamental reality revealed by decoherence theory. Every quantum interaction that makes these devices useful also contributes to the branching structure of parallel worlds. Each measurement performed by a quantum sensor, each calculation step in a quantum computer, each detection event in a quantum experiment potentially creates new branches in the multiverse where different outcomes unfold. This creates a fascinating philosophical paradox. The very technologies that might give us unprecedented power to explore and understand our universe are simultaneously creating countless parallel versions of that universe where different explorations and understandings emerge. Every quantum experiment splits reality into branches where scientists obtain different results. Every quantum computation creates parallel worlds where different problems are solved. In some sense, the development of quantum technology is accelerating the creation of parallel worlds. Every quantum computer that comes online, every quantum sensor that begins operation, every quantum experiment that collects data contributes to the constant branching that decoherence theory suggests is happening throughout the universe. We're not just passive observers of parallel world creation, we're active participants in it. But this doesn't diminish the value of quantum technology for our branch of reality. The quantum computers, sensors, and experiments in our timeline will provide insights and capabilities that benefit our specific version of human civilization. The fact that parallel branches might develop different technologies or reach different conclusions doesn't make our technological progress any less meaningful or useful. Or, as we near the end of our journey through the quantum multiverse, it's time to grapple with the profound philosophical implications of decoherence theory. If parallel worlds truly exist, if every quantum interaction creates new branches of reality where different outcomes unfold, then what does this mean for concepts like free will, moral responsibility, and the meaning of existence itself? The many worlds interpretation of quantum mechanics, supported by decoherence theory, presents us with a universe of infinite possibilities where every conceivable outcome eventually occurs in some branch of reality. This perspective can be both liberating and terrifying. On one hand, it suggests that every opportunity you've missed, every path you've wondered about, every alternative life you've imagined might be unfolding in parallel worlds. On the other hand, it raises disturbing questions about whether your choices matter, if all possible choices are being made simultaneously across the multiverse. Consider the weight of moral decisions in a quantum multiverse. If there are parallel branches where you make different ethical choices, where you help or harm others in ways that differ from your actions in this timeline, does moral responsibility become meaningless? Some philosophers argue that the existence of parallel worlds actually makes morality more important, not less. The version of you in this branch of reality is fully responsible for the consequences of your choices within this timeline, regardless of what parallel versions might be doing elsewhere. This perspective suggests that consciousness creates a kind of moral spotlight, illuminating one specific path through the quantum multiverse and making you responsible for the choices that define that path. You cannot control or even know about the parallel versions of yourself, but you remain fully accountable for the decisions that shape your particular branch of reality. The question of personal identity becomes equally complex in a world of parallel selves. Are you the same person as the version of yourself that existed a moment ago, before the latest quantum interactions created new branches? If parallel versions of you are making different choices and having different experiences, which one represents the real you? Decoherence theory suggests a fluid, dynamic view of identity, where the self is not a fixed entity, but a continuously evolving pattern of experiences and memories. Your identity in this moment represents the convergence of countless quantum events that led to your current state of awareness. You are simultaneously unique as the specific combination of quantum outcomes that created your timeline has never existed before, and universal as the physical processes that govern your existence operate according to the same fundamental laws throughout the multiverse. This has implications for how we think about death and continuation of consciousness. In a quantum multiverse, there might be branches where different biological processes unfold, where genetic mutations occur differently, where environmental factors affecting health and longevity vary in subtle ways. Some versions of you might live longer, others shorter, each following the consequences of quantum events that influenced biological systems at crucial moments. But decoherence theory suggests that your stream of consciousness, your subjective experience of being you, follows a single path through this branching structure. When biological processes in your timeline eventually cease to support consciousness, your awareness doesn't transfer to parallel branches where you might continue to live. Each branch contains its own version of consciousness, equally valid but completely separate from the others. This brings us to one of the most profound questions raised by decoherence theory. If parallel worlds exist but remain forever inaccessible, do they have any practical meaning for our lives? Some philosophers argue that inaccessible parallel worlds are meaningless, that we should focus only on the reality we can observe and influence. Others contend that the mere possibility of parallel worlds changes everything, altering how we think about probability, causation, and the nature of existence itself. The answer might lie in how these ideas change our perspective on the preciousness and uniqueness of our experiences. If your specific timeline is just one of countless parallel possibilities, this might make each moment more valuable, not less. The particular combination of quantum events that led to your current experience will never occur again. Your thoughts, feelings, relationships, and achievements exist in this exact form only within your branch of the multiverse. This uniqueness extends to all of human experience. The art, literature, music, and scientific discoveries of our civilization represent the specific cultural evolution that occurred in our branch of reality. In parallel worlds, different ideas might have emerged, different discoveries might have been made, different forms of beauty might have been created. But the achievements of our timeline belong uniquely to us, making them no less meaningful for being just one of many possible outcomes. Decoherence theory ultimately presents us with a universe that is both infinitely vast and intimately personal. Vast because it contains unlimited parallel worlds where every possibility unfolds. Personal because your conscious experience represents a unique path through this infinite landscape, a perspective that has never existed before and will never exist again. As you continue through your daily life, making choices and having experiences, remember that you're simultaneously one of countless parallel selves and the only version of yourself that you will ever know. The quantum interactions occurring in your brain and body right now are potentially creating new branches in the multiverse, but your consciousness remains anchored to this specific timeline, this particular sequence of quantum outcomes that created your unique perspective on existence. The parallel worlds revealed by decoherence theory may be forever hidden from direct observation, but they serve as a reminder of the extraordinary nature of conscious experience in a quantum universe. Every moment of awareness represents your mind's journey through the branching paths of infinite possibility, creating the continuous story of your existence one quantum interaction at a time. And if you're curious about what happens to consciousness itself in this strange quantum multiverse, you might find our previous exploration particularly thought-provoking. Quantum immortality terrifies scientists because consciousness might never end. It delves even deeper into the unsettling implications of parallel worlds for the nature of life, death, and the continuation of awareness across the quantum branches of reality. Until we meet again in this timeline, rest peacefully, knowing that somewhere in the vast expanse of parallel worlds, every version of the story you might have lived is unfolding in its own unique and beautiful way. The universe is far stranger and more wonderful than we ever imagined, and you are an essential part of that cosmic mystery, experiencing one precious thread in the infinite tapestry of existence. There's something deeply unsettling about the idea that your memories, those intimate records of your personal history, might be just one version of countless possible pasts unfolding across parallel timelines. Every cherished moment, every painful lesson, every random encounter that shaped who you are today exists only within your specific branch of the quantum multiverse. In adjacent realities, parallel versions of you might remember entirely different conversations, different outcomes to the same events, different paths through what you consider to be your unchangeable past. This brings us to one of the most profound mysteries of consciousness in a quantum multiverse, the nature of memory itself. When you recall a childhood birthday party, the feeling of your first kiss, or the conversation that changed your career path, you're accessing information that exists only within your timeline. These memories feel absolutely real and unchangeable because within your branch of reality, they are. But decoherence theory suggests that parallel versions of these same events, with subtly or dramatically different outcomes, are equally real in adjacent branches of the multiverse. Consider what happens when you form a memory. The process involves countless quantum interactions within your brain as neurons fire, proteins fold, and molecular pathways encode information into your neural networks. Each of these microscopic events is subject to quantum uncertainty, creating potential branching points where slightly different versions of the memory might be encoded. In most cases, the warm, wet environment of your brain causes rapid decoherence, ensuring that these quantum superpositions branch into separate worlds so quickly that your conscious experience follows a single, coherent timeline of memory formation. But the implications are staggering. Every memory you possess represents a specific quantum history, a unique sequence of molecular events that occurred in your particular branch of reality. Parallel versions of you might remember the same conversation going differently, the same decision leading to alternative outcomes, the same relationship unfolding along entirely different trajectories. Each version would feel equally certain that their memories represent the true history of their experiences. This quantum perspective on memory reveals something beautiful about the nature of personal history. Your past isn't a fixed sequence of events that happened in some objective timeline. Instead, it's a living construction of your consciousness, built from the specific quantum interactions that occurred in your neural networks as your brain processed and stored experiences. The story of your life is literally unique to your branch of the multiverse, a narrative that has never been told before and will never be told again in exactly the same way. But what about shared memories, the experiences you remember having with family members, friends, or loved ones? In our everyday understanding, these shared experiences seem to provide objective anchors for our personal histories. If you and a friend both remember the same event, surely that confirms it really happened in the way you both recall. Decoherence theory suggests a more nuanced picture. When you and another person experience an event together, your brains are both processing the same physical stimuli, but through separate neural networks that each undergo their own quantum processes. In most cases, the macroscopic aspects of the event create such strong classical correlations that both of your memories end up in the same branch of the multiverse, remembering consistent versions of what transpired. But there's always the possibility, however remote, that quantum processes in your respective brains might branch differently, creating parallel worlds where you remember slightly different versions of the same shared experience. In one branch, you might remember your friend saying something encouraging at a crucial moment. In another branch, they might have remained silent or said something entirely different. Both memories would feel equally real and valid to the versions of you experiencing them. This doesn't mean that shared memories are unreliable or that objective reality doesn't exist. Within each branch of the multiverse, the laws of physics ensure that events unfold in consistent, causal ways. The parallel worlds don't contradict each other. They simply represent different possibilities that emerged from the quantum uncertainty inherent in all physical processes, including those occurring in our brains. The quantum nature of memory also raises fascinating questions about nostalgia and regret. When you look back on your life and wonder, what if, you might be unconsciously sensing the existence of parallel branches where those alternative possibilities actually unfolded. The paths not taken in your timeline might be paths actively being explored by parallel versions of yourself in adjacent realities. This perspective can be both comforting and melancholy. Comforting because it suggests that every opportunity you missed, every chance you didn't take, every different choice you might have made is being explored somewhere in the vast expanse of parallel worlds. Melancholy because those alternative lives remain forever inaccessible to your consciousness, existing in branches of reality that diverged from yours through quantum processes you'll never be able to observe or influence. Recent research in neuroscience has begun to reveal just how dynamic and constructive human memory really is. Every time you recall a memory, you're not simply retrieving a stored file. Instead, you're reconstructing the experience from fragments of information distributed throughout your neural networks. This reconstruction process involves new quantum interactions, new opportunities for decoherence and branching, subtly altering the memory each time you access it. In a quantum multiverse, this means that your memories are not static records of the past, but living, evolving constructions that continue to branch into parallel versions each time you remember them. The story of your life is not just unique to your timeline, it's continuously becoming more unique as quantum processes in your brain create new variations of how you remember and interpret your experiences. As we journey deeper into the implications of quantum decoherence, we encounter what might be the most mind-bending aspect of parallel worlds: the realization that impossible events from the perspective of any single timeline become inevitable when viewed across the entire multiverse. Every outcome that has even the smallest quantum probability, no matter how remote, must occur in some branch of reality. This principle, known as the quantum principle of plenitude, suggests that the multiverse contains not just variations on familiar themes, but genuinely extraordinary and seemingly impossible worlds. Consider the quantum tunneling effect, where particles can pass through barriers that should be impenetrable according to classical physics. In our everyday experience, solid objects remain solid. You can't walk through walls, and baseballs don't spontaneously materialize on the other side of closed doors. But quantum mechanics tells us that there's always a tiny probability, impossibly small, but mathematically non-zero, that all the particles in your body could simultaneously tunnel through a solid barrier. In our branch of reality, this probability is so astronomically small that it would never occur even if you tried for billions of lifetimes. But in the vast expanse of the quantum multiverse, there must be branches where such impossible events actually happen. Somewhere in parallel reality, there might be versions of you who have experienced quantum tunneling through solid matter, living in worlds where the classical limitations we take for granted occasionally give way to pure quantum strangeness. This principle extends to every aspect of physical reality. There are branches of the multiverse where gravity occasionally reverses direction due to quantum fluctuations in space-time itself. There are worlds where objects spontaneously levitate, where energy appears from nothing, where cause and effect temporarily reverse their usual relationship. These aren't violations of physical law. They're extremely rare, but mathematically allowed outcomes of quantum processes that must occur somewhere in an infinite multiverse. The architecture of impossibility becomes even more fascinating when we consider biological systems. In our timeline, evolution follows predictable patterns constrained by chemistry, genetics, and environmental pressures. But in parallel branches, quantum events in crucial molecular processes might have led to entirely different evolutionary pathways. There might be worlds where photosynthesis evolved differently, where DNA uses alternative chemical bases, where consciousness emerged in organisms we would consider impossible. Some parallel branches might contain versions of Earth where the quantum processes governing genetic mutation led to dramatically different life forms. Others might have experienced different quantum events during the early formation of the solar system, leading to planets with alternative chemical compositions or orbital dynamics. The variations are not just biological, but astronomical, geological, and chemical. But perhaps the most profound implications of quantum plenitude concern the nature of consciousness itself. If awareness emerges from the complex quantum processes occurring in neural networks, then the branching structure of the multiverse must contain variations in consciousness that stretch far beyond our imagination. There might be parallel versions of human consciousness that experience reality in fundamentally different ways due to quantum differences in brain development or neural organization. This raises extraordinary questions about the boundaries of possible experience. In some branches of the multiverse, consciousness might have evolved with different sensory capabilities, different cognitive structures, different ways of processing information, and constructing models of reality. There might be versions of awareness that can directly perceive quantum superpositions, that experience multiple timelines simultaneously, or that have access to forms of knowledge impossible in our branch of reality. The quantum principle of plenitude also suggests that every story ever told, every work of fiction ever imagined, must have some correspondence to actual events occurring in parallel branches of the multiverse. The adventures described in novels, the scenarios depicted in films, the possibilities explored in thought experiments, all represent potential outcomes of quantum processes somewhere in the vast tree of parallel realities. This doesn't mean that fictional worlds exist exactly as described, but rather that the underlying physical processes that make such worlds possible must occur in some branches of the multiverse. Dragons might not breathe fire in parallel worlds, but there might be evolutionary pathways that led to large reptiles with chemical processes capable of producing combustible gases. Magic might not exist as supernatural force, but there might be branches where quantum effects operate differently, allowing phenomena that would appear magical from our perspective. The architecture of impossibility reveals something profound about the nature of creativity and imagination. When humans invent stories, explore hypothetical scenarios, or imagine alternative possibilities, we might be unconsciously tapping into the vast reservoir of parallel worlds that actually exist somewhere in the quantum multiverse. Our capacity for imagination might be, in some sense, a reflection of the infinite creativity of quantum reality itself. But this raises a fascinating paradox about knowledge and discovery. If every possible outcome occurs somewhere in the multiverse, then every possible scientific theory, every potential philosophical insight, every conceivable work of art must exist in some branch of reality. There are parallel worlds where scientists have made discoveries we haven't imagined, where philosophers have reached insights beyond our current understanding, where artists have created beauty we can't yet perceive. Yet these alternative forms of knowledge remain forever inaccessible to us, trapped in parallel branches that diverged from our timeline through quantum processes we cannot control or observe. We are simultaneously connected to infinite possibilities and isolated within our single branch of experience, able to imagine the vast architecture of impossibility, but never able to visit its most extraordinary rooms. In the quiet depths of quantum reality, time itself becomes something far stranger and more fluid than our everyday experience suggests. We typically think of time as a river flowing in one direction, carrying us from past through present toward future in an orderly, predictable sequence. But decoherence theory reveals time as something more like a vast delta, constantly branching and rebranching as quantum events create new tributaries of causality that flow parallel to each other but never again converge. This branching structure of time has profound implications for how we understand causality, the fundamental relationship between causes and effects that seems to govern our universe. In our classical intuition, each effect has specific causes that preceded it in time. But in a quantum multiverse, the relationship becomes more complex and beautiful. Every quantum event creates multiple branches where different causal chains unfold, each one internally consistent, but leading to systematically different outcomes. Consider something as simple as the radioactive decay of an atomic nucleus. In our classical understanding, we might say that the decay either happens or doesn't happen at any given moment. But quantum mechanics tells us that the atom exists in a superposition of decayed and undecayed states until decoherence creates branching. At the moment of branching, the universe splits into parallel timelines where different causal consequences follow from the different decay outcomes. In one branch, the decay might trigger a cascade of events. Perhaps the radiation from the decay influences a nearby chemical reaction, which affects the behavior of a biological system, which influences the decision-making of a conscious observer, which leads to actions that shape the course of future events. In the parallel branch where the decay doesn't occur, an entirely different causal chain unfolds, leading to systematically different outcomes that ripple forward through time. This branching causality creates what we might call an ecology of time, a complex system where different timelines coexist and evolve in parallel, each one nurturing its own unique sequence of events. Just as biological ecosystems contain countless interdependent species that shape each other's evolution, the temporal ecosystem of the quantum multiverse contains countless parallel timelines that emerge from the same quantum roots but develop their own distinct characteristics over time. The ecology metaphor reveals something beautiful about the relationship between parallel worlds. Just as species in an ecosystem don't compete directly across different geographical regions, parallel timelines don't interfere with each other. Once they've been separated by decoherence, each branch develops according to its own internal logic, following the causal chains that emerge from its specific quantum history. But there's also something melancholy about this temporal separation. In biological ecosystems, species can migrate between regions, adapt to new environments, and influence each other across vast distances and long time periods. Parallel timelines, once separated by decoherence, remain forever isolated from each other. The rich diversity of possibilities that exists across the quantum multiverse can never cross-pollinate or share insights between branches. This isolation has profound implications for the arrow of time itself. In our branch of reality, we experience time as flowing inexorably from past toward future, with entropy increasing and complexity emerging from simpler initial conditions. But other branches might have experienced different quantum events during the early moments. After the Big Bang, leading to universes with different physical constants, different evolutionary pathways, even different directions for the arrow of time itself. Some parallel branches might contain universes where time flows backward from our perspective, where entropy decreases rather than increases, where complexity dissolves into simplicity rather than emerging from it. These aren't violations of physical law, but alternative outcomes of the quantum processes that shape the fundamental structure of space-time during the earliest moments of cosmic evolution. The temporal ecology also raises fascinating questions about the relationship between memory and time. Our memories create a subjective arrow of time, a personal sense of flowing from past experiences toward future possibilities. But in a branching multiverse, memory itself becomes more complex. Each quantum interaction in your brain potentially creates branches where slightly different memories are formed, where your personal timeline develops different relationships to past and future. This suggests that your experience of time's passage might be unique not just to your individual consciousness, but to your specific branch of the quantum multiverse. Parallel versions of you might experience the same events unfolding in different temporal relationships, remembering the past differently and anticipating different futures based on the quantum history of their neural processes. Recent research in the foundations of quantum mechanics has begun to explore how the branching structure of parallel worlds might relate to the emergence of classical time. Some physicists propose that time itself emerges from the quantum process of decoherence, that the familiar temporal relationships we observe are consequences of how information flows from quantum systems into classical environments. In this view, the ecology of branching time isn't just a metaphor for how parallel worlds relate to each other. It's a literal description of how time itself comes into existence through quantum processes. Each branch of the multiverse doesn't just contain a different sequence of events. It contains its own version of time, its own temporal structure that emerges from the specific pattern of quantum interactions that define that branch. This perspective transforms our understanding of existence in the multiverse. You're not just living in one of many parallel worlds that happen to unfold at the same time. You're living in one of many parallel times, each with its own rhythm, its own relationship between cause and effect, its own way of connecting past experiences to future possibilities. The ecology of branching time reveals the quantum multiverse as a living, evolving system of temporal relationships, rather than a static collection of parallel worlds. Each moment of your conscious experience represents not just your location in space, but your location in a vast temporal landscape where countless alternative timelines branch and flow around you, each one nurturing its own unique version of how reality unfolds through the dimension we call time. Perhaps the most haunting aspect of quantum decoherence theory is not what it reveals about parallel worlds, but what it tells us about the profound silence that exists between them. In the vast expanse of the quantum multiverse, countless versions of reality unfold simultaneously, each containing conscious beings who wonder about the nature of existence, who seek connections with others, who long to understand their place in the cosmic order. Yet these parallel consciousnesses remain forever separated by an unbridgeable gulf of quantum isolation, unable to communicate, to share insights, or even to know of each other's existence. This silence between worlds is not empty space or absent time. It's something far more profound, the fundamental limit imposed by decoherence on information transfer between parallel branches of reality. Once quantum states become entangled with their environments and branch into separate worlds, the mathematical structure of quantum mechanics ensures that no signal, no message, no trace of information can pass between those branches. They exist in a kind of causal quarantine, forever parallel but never touching. Imagine the poignancy of the situation. Across the quantum multiverse, there might be versions of you who have solved problems that perplex you in this timeline. There might be parallel scientists who have made discoveries that could revolutionize medicine, parallel artists who have created beauty beyond your imagination, parallel philosophers who have found answers to questions that have haunted humanity for millennia. All of this knowledge, all of this wisdom, all of this potential for connection exists in abundance throughout the multiverse, yet remains completely inaccessible to you. The silence between worlds extends to every relationship you cherish. In parallel branches, different versions of your interactions with loved ones unfold, creating alternative histories of connection, understanding, and shared experience. There might be timelines where conversations went differently, where conflicts were resolved in other ways, where deeper intimacies were achieved or different paths of relationship emerged. These parallel relationships are as real and meaningful as the ones you experience in your timeline, yet they exist in complete isolation from your awareness. This quantum loneliness reveals something profound about the nature of consciousness in the multiverse. Your subjective experience of being aware of having thoughts and feelings and sensations represents just one thread in an infinite tapestry of parallel consciousnesses. Each thread is complete and meaningful in itself, but none can directly experience the patterns woven by the others. You are simultaneously one of countless minds and the only mind you will ever truly know. But there's something beautiful hidden within this isolation, something that makes the silence between worlds not just melancholy, but sacred. The very fact that these parallel worlds cannot communicate with each other ensures that each branch of reality develops its own authentic relationship with existence. Without the ability to compare notes with parallel versions of themselves, conscious beings in each timeline must find their own meaning, create their own values, discover their own truths about the nature of reality. This independence of parallel worlds creates what we might call quantum authenticity. Your thoughts, experiences, and insights are genuinely yours, not influenced by or dependent on the parallel versions that exist in adjacent branches of reality. The love you feel, the beauty you perceive, the understanding you achieve, all emerge from your unique path through the quantum multiverse without contamination from alternative possibilities. The silence between worlds also preserves the dignity of choice and consequence within each timeline. If parallel worlds could communicate, the weight of decisions might be diminished by the knowledge that all alternatives are being explored simultaneously elsewhere. But the isolation ensures that your choices have real meaning within your branch of reality, that the consequences of your actions matter in ways that are not diluted by the existence of parallel alternatives. Some physicists have speculated about whether the silence between worlds might not be absolute. They wonder if there might be subtle quantum interference effects that could, in principle, allow indirect detection of parallel branches. These effects would be extraordinarily weak and difficult to observe, but they might provide the faintest echo of communication between worlds that have diverged through decoherence. The search for such effects represents one of the most ambitious experimental programs in modern physics. Scientists are developing increasingly sensitive quantum interference experiments, looking for anomalous patterns that might indicate the influence of parallel branches on our timeline. So far, no conclusive evidence has been found, and decoherence theory suggests that any such effects would be buried beneath the noise of environmental interactions that constantly create new branching. But even if such communication were possible, it would likely be limited to the most abstract forms of information. You would never be able to have a conversation with a parallel version of yourself, never be able to share personal experiences or compare alternative life choices. The silence between worlds might be broken by faint mathematical whispers, but the deeper human longing for connection across parallel realities would remain unfulfilled. This limitation might actually be essential to the stability of conscious experience. If parallel worlds could communicate freely, the resulting confusion of multiple timelines, alternative memories, and contradictory experiences might make coherent consciousness impossible. The silence between worlds might be not just an unfortunate consequence of quantum mechanics, but a necessary condition for the existence of stable, meaningful awareness. The profound quiet that surrounds your timeline, the absence of voices from parallel worlds, creates the space within which your unique consciousness can exist and flourish. In this silence, your thoughts have room to develop, your experiences can accumulate into meaningful patterns, your relationships can deepen without interference from alternative versions. The isolation that seems so melancholy from one perspective becomes, from another, the foundation for the authenticity and significance of your existence. In the hushed corridors of the quantum multiverse, there exists something that resembles an infinite library, vast beyond imagination, containing not books but entire worlds. Each branch of reality represents a unique volume in this cosmic collection, telling the story of what unfolds when quantum possibilities crystallize into specific outcomes. Unlike any earthly library, this one contains every possible story that the laws of physics allow, every variation on the themes of existence that can emerge from the fundamental quantum processes that govern reality. The architecture of this infinite library follows the branching structure of decoherence itself. At each quantum measurement, each moment when microscopic possibilities become macroscopic realities, new wings are added to the library. New shelves extend into dimensions of possibility we can barely conceive, lined with volumes that tell stories of worlds that differ from ours in ways both subtle and profound. Some of these worlds vary from ours by the outcome of a single quantum event. Others have diverged so far that they would be unrecognizable to visitors from our branch of reality. Consider the section of this library that contains variations on your own life story. In one volume, you might find the timeline where you made different choices at crucial moments, where quantum processes in your brain led to alternative decisions that shaped your path through life. Another volume might contain the story of a world where quantum events during your early development led to different talents, different interests, different ways of understanding and interacting with reality. But the library extends far beyond personal variations. There are sections devoted to alternative histories of human civilization, where quantum events during crucial moments of discovery, conflict, and cultural development led to different trajectories for our species. Some volumes tell of worlds where different scientific principles were discovered first, leading to alternative technologies and ways of understanding the universe. Others contain stories of civilizations that developed different forms of art, different philosophies, different approaches to the fundamental questions of existence. The The scientific section of this infinite library would be particularly fascinating to explore, if such exploration were possible. It contains volumes describing worlds where quantum mechanics itself was discovered differently, where alternative interpretations of the same mathematical formalism led to different experimental programs and different insights into the nature of reality. There might be branches where scientists developed more complete theories of quantum gravity centuries before our timeline, or where entirely different approaches to understanding consciousness emerged from alternative traditions of inquiry. In the philosophy wing, we would find explorations of questions that have never been asked in our timeline, insights that emerged from different cultural contexts and different ways of thinking about the nature of existence. Some volumes might contain solutions to problems that perplex philosophers in our world, while others might reveal that our most cherished insights are merely local truths that don't apply across all branches of reality. The artistic collection in this infinite library would contain forms of beauty that no consciousness in our timeline has ever imagined. Music based on alternative mathematical relationships between frequencies, visual arts that exploit different properties of light and perception, literature that explores narrative structures impossible in our branch of reality. Each volume would represent not just alternative individual creativity, but alternative cultural evolution that led to different aesthetic possibilities. But perhaps the most profound section of this library would be devoted to alternative forms of consciousness itself. If awareness emerges from quantum processes in neural networks, then the branching structure of the multiverse must contain variations on consciousness that stretch far beyond our current understanding. Some volumes might describe forms of awareness that experience multiple timelines simultaneously. Others might contain consciousness that perceives quantum superpositions directly. Still others might describe awareness that exists in entirely different relationships to space, time, and causality. The tragedy and beauty of this infinite library is that each volume can only be read from within its own world. The conscious beings in each branch of reality have access only to their own story, their own version of how quantum possibilities crystallized into specific experiences and insights. The vast wealth of knowledge, beauty, and understanding that exists throughout the multiverse remains forever locked away behind the barriers created by decoherence. This creates a profound form of cosmic irony. The universe contains, in principle, solutions to every problem, answers to every question, forms of beauty and meaning beyond our wildest imagination. All of this exists with absolute certainty somewhere in the quantum multiverse, yet the very physical processes that create this infinite diversity also ensure that each branch remains isolated from all the others, unable to share insights or learn from alternative approaches to existence. Recent work in quantum information theory has begun to explore whether there might be subtle ways to access information from parallel branches, perhaps through careful analysis of quantum interference effects, or through the development of quantum computers that could somehow detect the influence of parallel calculations. But even the most optimistic proposals suggest that any such access would be extremely limited and indirect, more like detecting the faint shadow of parallel worlds than actually visiting them. The infinite library metaphor reveals something important about the nature of knowledge and discovery in our timeline. Every insight we achieve, every truth we uncover, every moment of understanding we experience represents a unique contribution to the cosmic collection of knowledge. Our discoveries are simultaneously insignificant, because parallel versions exist throughout the multiverse, and precious beyond measure, because they represent the only versions accessible to our branch of reality. This perspective can be both humbling and inspiring. Humbling because it suggests that our greatest achievements and deepest insights are just single volumes in an infinite collection, no more or less valid than countless alternatives. Inspiring because it reveals that every moment of understanding, every creative breakthrough, every act of discovery contributes something genuinely unique to the vast tapestry of knowledge that exists across the quantum multiverse. The infinite library of what might be stands as a testament to the creative power of quantum reality itself. It reminds us that existence is not a single story unfolding through time, but an infinite collection of stories exploring every possible variation on the themes of consciousness, experience, and understanding. Chapter 16. The Quantum Mirror of Self. There's a moment that occurs to every person who truly grasps the implications of quantum decoherence theory, a moment that feels like standing before an infinite mirror that reflects not your image, but your infinite possibilities. In that reflection, you see not just who you are, but glimpses of who you might have been, who you could become, and who you are becoming in countless parallel branches of reality. It's both the most humbling and the most magnificent realization that consciousness can achieve. The understanding that your identity is simultaneously unique and infinite, precious and countless, singular and multiplied across the vast expanse of quantum possibility. This quantum mirror reveals something profound about the nature of selfhood in a branching multiverse. The person you recognize as you in this moment represents just one specific path through the quantum landscape of possibility. Every decision you've made, every experience that shaped your personality, every random quantum event that influenced your neural development has contributed to creating this particular version of your identity. But in parallel branches, alternative versions of these same formative processes have created systematically different versions of who you are. The implications stretch far beyond philosophical speculation. Consider the quantum processes occurring in your brain as you read these words. Neural networks fire in complex patterns, neurotransmitters flow across synaptic gaps, and molecular machinery processes the information streaming through your consciousness. Each of these processes involves quantum mechanics at its most fundamental level, creating countless opportunities for decoherence and branching. In this very moment, as your brain processes these ideas about parallel worlds and quantum identity, there might be branches of reality where your neural responses are subtly different. Perhaps in one branch, a particular quantum event in your hippocampus leads to these concepts being encoded into memory with slightly different emotional associations. In another branch, quantum processes in your prefrontal cortex might create different patterns of logical analysis, leading to alternative insights or concerns about the implications of parallel worlds. Each of these variations would create a version of you that is recognizably yourself, yet distinctly different in its internal experience. The alternative versions would share your foundational memories, your basic personality structure, your core relationships, and commitments, but they might differ in their intuitive responses to ideas, their emotional reactions to experiences, their subtle preferences, and inclinations that shape the flow of consciousness from moment to moment. This multiplicity of self raises profound questions about personal responsibility and moral development. If there are parallel versions of you making different ethical choices, developing different character traits, following different paths of moral growth. Which version represents the real you? Quantum Decoherence Theory suggests that all versions are equally real, equally valid expressions of the possibilities inherent in your fundamental nature as it encounters different quantum outcomes. But this doesn't diminish the significance of your choices or the authenticity of your moral development in this timeline. Each version of you across the quantum multiverse faces the same fundamental challenge: how to live meaningfully and ethically within the constraints and opportunities of their specific branch of reality. The choices you make, the character you develop, the relationships you nurture, all represent your unique contribution to the vast tapestry of human experience unfolding across parallel worlds. The quantum mirror also reflects something beautiful about the nature of human potential. In our everyday experience, we often feel limited by our circumstances, our talents, our opportunities. We wonder about roads not taken, possibilities not explored, aspects of ourselves that never had the chance to develop. But the branching structure of the multiverse suggests that every unrealized potential might be finding expression somewhere in the vast network of parallel realities. That artistic talent you never pursued might be flourishing in a branch where quantum events led you to different early experiences or educational opportunities. That relationship that never quite worked out in this timeline might be thriving in a parallel world where different quantum processes led to different communication patterns or emotional responses. The career path you abandoned might be reaching fulfillment in a reality where alternative quantum events influenced your decision-making processes at crucial moments. This perspective can be simultaneously liberating and melancholic. Liberating because it suggests that no aspect of your potential is truly lost, that every possibility is being explored somewhere in the quantum multiverse. Melancholic because those alternative versions of your potential remain forever inaccessible, existing in branches of reality that have become decorrelated from your timeline through the inexorable process of decoherence. Recent research in neuroscience and psychology has begun to reveal just how dynamic and malleable human identity really is. Our personalities, our preferences, our ways of thinking and feeling are not fixed characteristics, but continuously evolving patterns that emerge from the complex interactions between our brains and their environments. Every experience, every interaction, every moment of learning or growth involves quantum processes that could, in principle, create branching points where different versions of your identity emerge. But the warm, wet environment of your neural tissue ensures that these quantum superpositions decohere rapidly, creating the illusion of a single, continuous stream of consciousness. You experience yourself as a unified identity flowing smoothly through time, unaware of the countless parallel versions that branch off from your timeline through quantum processes occurring beneath the threshold of conscious awareness. This unified experience of selfhood might be one of the most remarkable achievements of biological evolution. In a quantum universe, where everything is constantly branching into parallel alternatives, somehow the complex systems we call brains have developed the ability to create coherent, continuous experiences of identity. The quantum mirror might reflect infinite versions of who you are, but your consciousness experiences only one reflection at a time, creating the stable sense of self that makes meaningful existence possible. The quantum nature of identity also has implications for how we think about memory, learning, and personal growth. Every time you form a new memory, every moment of insight or understanding, every experience that contributes to your development as a person involves quantum processes that could create branching. The person you become through these experiences is just one of many possible outcomes of your interaction with reality, shaped by quantum events too subtle and numerous to track or predict. In the grand concert hall of existence, the quantum multiverse performs an eternal symphony of staggering complexity and beauty. Imagine, if you will, countless orchestras playing simultaneously in adjacent performance spaces, each performing variations on the same cosmic composition. Some orchestras play the piece exactly as written, while others improvise subtle variations on familiar themes. Still others venture into entirely different musical territories, exploring harmonies and rhythms that would sound alien to ears accustomed to more conventional arrangements. This musical metaphor captures something essential about how parallel worlds relate to each other through the process of quantum decoherence. Each branch of reality contains its own complete, internally consistent version of existence, like a fully orchestrated piece of music that tells a coherent story from beginning to end. But these musical narratives exist in parallel, never able to hear each other's performances, never able to appreciate the subtle variations and bold innovations that neighbouring orchestras are exploring. The symphony began at the moment of the Big Bang, when the universe existed in a quantum superposition of all possible initial conditions. As cosmic evolution proceeded and quantum measurements occurred throughout the expanding cosmos, the universal composition began to branch into countless variations. Some branches followed nearly identical musical themes, differing only in the timing of a single note, or the slight variation in a particular harmony. Others diverged dramatically, developing entirely different musical structures as fundamental constants, physical laws, or initial conditions took on alternative values. In our branch of the cosmic symphony, the music has evolved to include the emergence of stars and planets, the development of complex chemistry, the appearance of life, and eventually the awakening of consciousness capable of contemplating its own existence. But in parallel movements of the same cosmic composition, the music might have evolved very differently. Some branches might contain universes where different physical constants led to alternative stellar evolution, creating cosmic environments where entirely different forms of complexity could emerge. The biological section of this symphony would be particularly rich in variation. In our musical timeline, evolution has composed a magnificent piece featuring carbon-based biochemistry, DNA-encoded genetics, and nervous systems that give rise to consciousness. But quantum events during crucial moments of early evolutionary history might have led to completely different biological compositions in parallel branches. Some might feature life based on alternative chemical foundations. Others might have developed entirely different approaches to information storage and processing. Still others might have evolved forms of consciousness that experience reality in ways we can barely imagine. The human movement within this biological section contains its own infinite variations. Each person represents a unique melodic line within the larger human composition, shaped by the specific sequence of quantum events that influence their development from conception through their current moment of existence. But in parallel branches, alternative quantum events during crucial developmental periods might have created systematically different versions of each human melody. Consider the neural symphony occurring within your own consciousness as you contemplate these ideas. the pattern of neurons firing in your brain creates a unique musical phrase within the larger human composition, a phrase that has never been played before and will never be repeated exactly. But quantum processes in your neural networks are simultaneously creating parallel variations on this mental melody, branches where your thoughts develop along slightly different pathways, where your emotional responses follow alternative harmonic progressions. The tragedy and beauty of this cosmic symphony is that each orchestra can only hear its own performance. The musicians in our branch of reality can only appreciate the music that emerges from our specific quantum history, unaware of the countless variations being performed simultaneously in parallel concert halls. We experience our version of existence as complete and meaningful in itself, which it is, but we remain deaf to the alternative harmonies that might be equally beautiful or profound. This musical isolation creates what we might call harmonic authenticity within each branch of reality. Without the ability to compare their performance to alternative versions, the musicians in each orchestra must find their own way to create beauty and meaning through their art. The music that emerges is genuinely creative, genuinely expressive, genuinely valuable, even though similar but distinct compositions are being performed in countless parallel venues. Recent theoretical work in cosmology has begun to explore whether the different branches of the multiverse might be connected by subtle resonances, like distant orchestras whose performances occasionally synchronize through barely detectable acoustic coupling. Some physicists speculate about whether quantum interference effects might create faint harmonies between parallel worlds, allowing the faintest echoes of alternative compositions to influence the music in our branch of reality. But even if such resonances exist, they would be far too subtle to allow direct communication between parallel orchestras. The cosmic symphony would remain fundamentally fragmented, with each branch developing its own unique approach to the themes of existence, consciousness, and meaning. The resonances might create mysterious harmonies that add depth and richness to the music within each branch, but they could never allow musicians in different orchestras to collaborate directly or share their alternative interpretations of the cosmic composition. The symphony metaphor also reveals something profound about the role of consciousness within the quantum multiverse. Conscious beings like ourselves are not just passive listeners to the cosmic music. We are active musicians contributing our own melodies to the grand performance. Every thought we think, every choice we make, every moment of awareness we experience adds new notes to the symphony unfolding within our branch of reality. But our musical contributions are simultaneously creative and constrained. We are free to improvise within the harmonic structure established by the quantum history of our timeline. But we cannot venture outside the musical possibilities that decoherence has made available within our branch of the multiverse. Our creativity is real and meaningful, but it unfolds within boundaries established by quantum processes we can neither control nor fully understand. The cosmic symphony continues to evolve, with new movements being composed moment by moment as quantum measurements create fresh branching points throughout the multiverse. Each branch explores its own musical possibilities, developing its own themes and variations on the fundamental composition of existence. And while we can only hear the music of our own timeline, the knowledge that countless other performances are unfolding in parallel adds a profound depth to our appreciation of the particular symphony we have the privilege to experience. In the landscape of quantum reality, there exists something resembling an infinite garden where every possible path branches into countless alternative routes, each leading to different destinations through the terrain of existence. This is not a metaphorical garden, but a precise description of how quantum decoherence creates the branching structure of parallel worlds. At every quantum measurement, reality forks like a path in this cosmic garden, creating new routes that will never again converge, never again share the same scenic vistas, or arrive at the same destinations. Walking through our section of this vast garden, we follow just one of the infinite number of pathways available to conscious experience. Every step we take represents a quantum event that has crystallized into classical reality. Every turn we make reflects a choice between alternatives that has become locked into our timeline through the process of decoherence. But surrounding our path, separated from us by barriers of quantum isolation that can never be crossed, like countless other walkways where parallel versions of ourselves explore different routes through the same fundamental landscape. The topology of this garden is unlike anything that exists in ordinary space. Paths can branch at any moment, creating forks where different quantum outcomes lead to systematically different futures. Some branches remain nearly parallel for vast stretches, separated only by minor variations in how quantum events unfold. Others diverge dramatically from the moment of branching, leading through entirely different regions of possibility space toward destinations that would be unrecognizable to travelers from our timeline. Consider the branching that occurred during the early moments of your life, when quantum events in developing neural networks created the foundation for your eventual consciousness. At countless points during embryonic and early childhood development, quantum processes could have unfolded differently, creating branches where alternative versions of your personality, talents, and cognitive capabilities emerged. Some of these alternative selves would be remarkably similar to who you are now, differing only in subtle preferences or inclinations. Others might have developed along completely different trajectories, becoming people you would hardly recognize as versions of yourself. The paths that branch away from yours in this garden are not empty or lifeless. Each one supports its own rich ecosystem of experiences, relationships, and discoveries. In branches where different quantum events shaped your early neural development, alternative versions of you are walking through landscapes of possibility that share the same fundamental structure as yours, but offer completely different vistas of experience and understanding. The gardeners tending this infinite space are the quantum fields themselves, constantly creating new pathways as measurements occur throughout the universe. Every photon that interacts with matter, every particle that decays, every quantum system that becomes entangled with its environment contributes to the endless proliferation of branching paths. The garden grows more complex with each passing moment, its network of possibilities expanding faster than consciousness can map or imagination can encompass. But perhaps the most remarkable feature of this quantum garden is how each path maintains its own internal coherence while remaining forever separated from all the others. The route you're travelling feels complete and meaningful because it is complete and meaningful within its own branch of reality. The relationships you've formed, the knowledge you've gained, the beauty you've experienced all exist as genuine features of your particular pathway through possibility space. Yet there's something both haunting and wonderful about knowing that parallel paths exist where different versions of these same relationships, different forms of knowledge, different expressions of beauty are unfolding simultaneously. In adjacent branches of the garden, conversations with loved ones might have taken different turns, leading to deeper understanding or alternative forms of connection. Scientific discoveries might have proceeded along different trajectories, revealing aspects of reality that remain hidden in our timeline. Artistic expressions might have emerged that explore forms of beauty we've never imagined. The branching structure of this garden also reveals something profound about the nature of possibility itself. Every path that exists represents not just what has happened, but what can happen given the fundamental laws that govern quantum reality. The garden contains every possible variation on the themes of existence that quantum mechanics allows, from the subtle differences created by single quantum events to the dramatic alternatives that emerge when entire chains of causation unfold differently. Walking through your section of this vast garden, you carry with you the accumulated wisdom of your particular journey through possibility space. Every challenge you've overcome, every insight you've gained, every moment of growth you've experienced represents knowledge that exists uniquely within your branch of reality. This wisdom cannot be shared directly with the parallel travelers on adjacent paths, but it contributes something irreplaceable to the total landscape of understanding that exists across the quantum multiverse. The paths in this garden are not predetermined routes laid out in advance, but living trajectories that emerge moment by moment as quantum possibilities crystallize into classical realities. Each step you take helps create the path itself, contributing to the ongoing growth and evolution of the branching structure that defines the garden's topology. You are simultaneously a traveller exploring pre-existing possibilities and a creator participating in the continuous expansion of what's possible. And so we arrive at the end of our quiet journey through the quantum multiverse, where parallel worlds bloom like flowers in an infinite garden, each one real and beautiful, yet forever beyond our reach. We've walked together through the mathematics of hidden realities, witnessed the birth of countless worlds in the blink of an eye, and contemplated what it means to exist as one conscious thread in a vast tapestry of parallel possibilities. The profound truth that quantum decoherence reveals is both humbling and magnificent. Every moment of your existence creates countless versions of reality, each one branching away into its own timeline where different outcomes unfold. Yet the very process that creates these parallel worlds also ensures they remain eternally hidden, separated by barriers of quantum isolation that can never be crossed. You are simultaneously one of infinite selves and the only version of yourself you'll ever truly know. Perhaps that's the most beautiful paradox of all. In a universe where every possibility exists somewhere, your particular path through the quantum landscape becomes not less meaningful, but infinitely precious. Your thoughts, your relationships, your moments of wonder and discovery exist in this exact form nowhere else in the entire multiverse. You are living one unique story in an infinite library of possibilities. So tonight, as you drift towards sleep, remember that somewhere in the vast expanse of parallel realities, every version of the life you might have lived continues to unfold. But here, in this timeline, in this moment, you are exactly where the quantum universe intended you to be. Rest peacefully in the knowledge that your existence is both one thread in an infinite weave and utterly irreplaceable in the cosmic symphony of consciousness itself.